In this video, we will be discussing hydrogen bonding. Hydrogen bonding is an interesting subset of dipole-dipole interactions that only occurs when you have a nitrogen, oxygen, or fluorine present attached to a hydrogen. This is a bit of a misnomer. This is not a formal bond, but it's just a stronger version of the dipole-dipole attractive force. When you have a hydrogen attached to either a nitrogen, oxygen, or a fluorine, the difference in electronegativity creates an extreme dipole. Now, for example, here with water on the left, when we have a hydrogen come close to an oxygen, the difference in electronegativity causes an extreme attraction. Again, this is not a formal bond, but because it is so much stronger than any other dipole-dipole interaction, it's called a hydrogen bond. We also see this in ammonia and hydrogen fluoride. We have this extra attractive force between these different molecules. Now, it doesn't have to be between a hydrogen, or it doesn't have to be between a water and another water molecule, or between ammonia and just between hydrogen fluoride molecules. It can also exist between different molecules. For instance, we can have the hydrogen on ammonia attracted to the oxygen on water, and vice versa. We can have more than one hydrogen bond between molecules, such as an acetic acid. And if the hydrogen in salicylic acid lines up just right, we can actually have an intramolecular hydrogen bond. Now, hydrogen bonding, again, isn't particularly strong. It's just stronger than your standard dipole-dipole interaction, and it's not a formal bond. But if you get enough of these hydrogen bonds, you can actually create an extremely strong attraction. For instance, hydrogen bonding is what gives cellulose its rigid structure, and this is what also keeps the two strands of DNA connected together at each base pair. You have between 2 and 3 hydrogen bonds between each base pair. That can really add up. Hydrogen bonding is also responsible for the crystalline structure of ice and what gives a snowflake its 6-fold radial symmetry. Now let's take a look at one of the consequences of hydrogen bonding. If we take a look at boiling points based on a period of the element, for instance here we have group 16, we have sulfur, selenium, and tellurium, making hydrogen sulfide, hydrogen selenide, and hydrogen telluride. We notice that as we go down the periodic table and we increase the molecular weight, our boiling point goes up. Now, what's at the top of this group? Well, we have oxygen. This would be water right here. This is the approximate expected boiling point of water, somewhere between -150 and -100, about -80 degrees. We know this isn't true. Same goes for group 17 and group 15. We would expect the boiling point of hydrogen fluoride to be about -120 and the boiling point of ammonia to be about -130. This actually isn't the case. These extremely atypical boiling points as you increase molecular weight down a group, well, this is because of hydrogen bonding. The additional attractive force of hydrogen bonding in each one of these molecules is responsible for its high boiling point. It requires a lot more energy to break not only the standard dipole-dipole interaction, but the additional hydrogen bonding. And the more hydrogen bonding structures you have in your molecule is also going to increase the boiling point and the general attractive forces. For instance, if we have propanol versus propylene glycol and glycerol, as we add more hydroxides, or more alcohol groups in this case, we increase the number of places where you can experience hydrogen bonding, and therefore you're going to increase the attractive forces, and it's going to require more heat in order to boil. So you're probably thinking, well, we're also adding more molecular weight. Perhaps that's also responsible for increasing the boiling point. Well, yes, that is true. We are increasing the molecular weight, but let's take a look at an example where we don't increase the molecular weight that much. Here we have N-pentanol, 1,2-butane diol, and glycerol. In each case, the molecular mass does not increase that much, but we have added another alcohol group that can perform hydrogen bonding. So this additional increase in molecular mass for each one of these molecules cannot possibly explain the dramatic increase in boiling point for each one. This is all due to the increased number of places for hydrogen bonding to occur and increasing the attractive forces. So, a recap on hydrogen bonding. Hydrogen bonding is a subset of dipole-dipole interaction. It is an extra strong attraction between hydrogen atoms attached to a nitrogen, oxygen, or fluorine, and another nitrogen, oxygen, or fluorine atom on another molecule, or within the same molecule. And these are responsible for unusually high melting points and boiling points, and increase in intermolecular forces.